Okay, so in lecture 1, we will be focusing on number systems. And the goal is to do two things. One, how do you represent numbers in a variety of forms in different number systems? And two, how do you do arithmetic with those numbers? We will start off with the number system that everybody knows about, the decimal number systems. Now, the decimal number system, everybody knows about that because we have been seeing 10 fingers and 10 toes, right? So that we can count anything on using our fingers. It's very easy for humans to understand decimal representation. What does decimal mean? Decimal means 10. So when I say decimal number system, I'm talking about a number system that has 10 digits or 10 symbols. So the symbols that are there in decimal number system are 0 through 9. Any number in decimal number system can be represented using these 10 symbols, 0 through 9. There's a question in the chat box. Are there words for tenths and hundredths place, etc. in binary and hex? No, there are no common terms like that. So there are no words like that. So all right, let's move on to come back to this. So that's our most common number system, the decimal number system. And it turns out you can represent any number in the decimal number system using positional number notation, also called as positional significance. What do we do in that? We just take the number and we multiply each digit by its weight. For example, 6 is the least significant digit. I'm going to be using LSD, least significant digit, for 6 here, and for 2 I have the most significant digit here. So how do I get to 246? How can I express 246 in a positional significance notation? Well, I take my least significant digit and I multiply that by 10 raised to 0. And then the next one gets multiplied by the next higher power of 10, and the next number gets multiplied by the next higher power of 10. And then we add everything up. In general, I can express that as any number n can be expressed as a summation, the addition of each digit multiplied by 10 raised to I, where I is essentially your position. So n, any number, right? In our previous example, n was 246. That is your summation sign. So that's your addition. N sub I, in our example, it was 2, it was also 4, it was also 6. And our I was any number, any integer that was greater than or equal to 0. And it was an integer. The greater than or equal to 0 works for numbers like 246, integers. It doesn't work for fractions. So on this slide, well, for until now, we have been talking about integers. We are going to also add on fractions to this. But more importantly, we have been focusing on unsigned numbers. Notice we have not talked about whether that 246 is positive or negative. We are dealing with unsigned integers and fractions to begin our course. And then halfway through our lecture 1 on number systems, we will start talking about signed representations. Now, let's come back to this. By the way, this decimal number system has 10 symbols, so we should have a particular name for the 10. And there is. We call it the base. The base of this number system is 10. Base 10. Also called as radix 10. Also called as the decimal number system. Now, as you go to the negative powers of I, you essentially get decimal fractions. So for example, if you wanted to express 0.35 in a positional number notation, what would you do? You would multiply 3 with 10 raised to negative 1, and you would multiply 5 with 10 raised to negative 2. Add them up, you would get your number, right? So as you're moving left from the decimal point, you are increasing I, and I is an integer. And as you are going right, you are decreasing your exponent. Negative 1, negative 2, negative 3, and so on. How about both of these combined, right? How do you express 246.35? It's a decimal fraction. How did I know that it's a decimal fraction? I put a 10 as the subscript of the number. Now, a quick note here. Some people might write the same number as this. Some people might write the same number as this. Some people in a very in hurry might write it like this. You see the problem here? There is no way to distinguish between the number and the radix of the number. It's very ambiguous, absolutely. So even though this is okay, this is absolutely not okay, this is questionable, I like this. By providing the parentheses around the number and then putting a 10 as the subscript, we get rid of that ambiguity, right? So I like to represent my numbers this way, right? So it's very clear what the number is and what is the base. Let me get rid of this now and talk about how do we do this, right? So 246.35. By the way, what do I call this point? That is a decimal point. Meaning there could be a binary point. There could be a hexadecimal point, meaning there could be an octal point. But right now we are talking about decimal number system and there is a point, so that's a decimal point. Now coming back to the example that we were doing, 246.35. So you do 2 times 10 to the 2 plus 4 times 10 to the 1 plus 6 times 10 to the 0 plus 3 times 10 to the negative 1, 5 times 10 to the negative 2. And that's exactly how we represent this particular fraction. This is an unsigned fraction, and we have represented it using the positional number notation. And we see the 10 everywhere. What does that mean? That means that if I changed the base, all I would be changing are these numbers. If I change that. let's move on to the binary number system that we will talk about the most in this course, which is the binary representation or the binary number system. Who loves binary? If humans love decimal, who loves binary? Robots, sure, yes. Computers love binary, right? So computers love binary number system because the signals, the electrical signals, bebop, yes, the electrical signals that are involved in binary number system are off and on. And we can use a 0 to indicate off and a 1 to indicate on. And we can actually represent any real phenomena using just these two numbers, 0 and 1. There are 10 types of people. I should actually say there are 10 type of people, those who like binary and those who don't. Absolutely. So computers understand the language of zeros and ones, and we are trying to communicate or write programs or control computers so that they can do all the instructions that we would want them to do. So we need to worry about zeros and ones. A bunch of zeros and ones, what do you call it? You call it the machine language, right? The language that the machines understand. But if that number system is going to be used so much, then we also need to worry about how do you represent numbers, unsigned, signed, integers and fractions in that number system. And it is binary. Binary means 2, and it has to have 2 symbols. What are those symbols? The symbols are 0 and 1. Now, if you notice, we can also represent a number using positional number notation in binary. What changed? N is the number. I'm still doing addition. I'm still taking each. What should I call n sub I in this? Well, let me go back here. What did I call n sub I here? I called it a digit. What should I call n sub I over here? Binary digit or bit. Yes, bidget. So n sub I belongs to 0 and 1, and we have the radix raised to I as opposed to having 10 raised to I. Now with binary you have 2 raised to I, and as we go further to octal and hexadecimal number systems, we will have 8 raised to I or 16 raised to I. Next, how do you convert 111001? The base is 2 or the radix is 2, so that's how I know it's a binary number, and I want to convert binary to decimal. All right, Arnav says there's a petition to make bit bidget. All right. We will try to call, I'm going to try my best to call a bit a bidget as much as possible. All right, you guys got it. I cannot, promise it, but I will try my best. So how do you convert a binary number? My internet is 30 megabits per second. That's my binary number, and I know it's binary because the base is 2, and all the symbols in this number are zeros and ones, so I know for sure that it can belong to a binary number system. By the way, can this number belong to a decimal number system? Yeah, absolutely, right. So it is absolutely okay, right? Because 1 and 0, they are also belonging to the decimal number system, right? How do I do that? Well, I take each digit and I'm going to multiply it with increasing powers of 2. So for example, I'm going to take my least significant digit and multiply it with 2 raised to 0. And as I move left, I'm going to take each digit and multiply it with increasing powers of 2. Why 2? Because it is conversion from binary to decimal. Finally, I get to the most significant digit, MSB, LSB. That's my 1. So that's 1 times 2 to the 5. I expand them out, I add things up, and I get 57 in the decimal number system. That's very easy, right? Take each digit, multiply it with increasing powers of 2 if you were going from binary to decimal, multiply, and then add. Once you add, you are going to get the number in decimal number system. What do you think I should do to go back? If I was asked to convert 57 to binary, what should I do? Divide by 2 and take remainder. Perfect. If I can go from binary to decimal, I can also go from decimal to binary. From binary to decimal was multiply by increasing powers of 2. From decimal to binary should be exactly the opposite. Keep dividing by 2 and record the remainders. Which leads us to this slide, which is converting decimal to binary. All we need to do is successive division. So in order to convert 57 to binary, we are going to keep dividing the number by 2, and every time we divide the number by 2, we will record the remainder. And because we are dividing by 2, it has to be a 0 or a 1. And we keep doing that until we get a quotient of 0. But when we have to write out the answer in the binary number system, we are going to go backwards. We are going to actually read the remainders in the opposite manner in which they were computed. So the number in binary would be 111001. Let's do an example. And this is sort of a very involved example, because I not only have a binary number that needs to be converted to base 10. So I'm going from base 2 or binary or radix 2 to a decimal number system. Andrew, even though that is okay, I would discourage that notation for now. I would encourage you guys to represent numbers in this manner. So in this example, we are converting a binary number. It's actually a binary fraction. I want to find out what its value is in decimal number system. What should I call this point? Binary point. Yes. Now, these ones and zeros eventually, say you're trying to store a number on disk, right? So you're trying to store a bunch of zeros and ones in memory. Do you save the binary point or you don't save the binary point? No. So if you don't save the binary point, don't save it. Yes, you're absolutely right. You don't save the binary point. Then how would I know that this is a fraction? How would I know? Add another bit somewhere, maybe. Okay. So if you think about a 32-bit computer or a 64-bit computer, there are two very famous standards. IEEE 32-bit single precision format and IEEE format for 64-bit double precision format. Those formats that are accepted by that particular computer, that means that every number will be accepted and represented in those formats. The format itself will have a bunch of 32s or a bunch of 64 zeros and ones. But the format itself will have specific number, a specific representation for the decimal part or the integer part and then the fraction part. So the format dictates where the binary point is going to be. It is not stored in an explicit manner. It is implicit binary point. All right, let's come back to this conversion here. So if I need to go from binary to decimal, in fact, if I need to go from any number system to decimal number system, I will use positional significance. Any number system to decimal, I will use positional significance, which means all I'm going to do is I'm going to note down the powers of 2 that I need to multiply with each digit. So for example, this guy is going to be 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3. What are those? Those are the weights of those positions. And then of course, as we go to the right of the binary point, you have decreasing powers of 2. And then I'm going to simply multiply, too big. I'm going to simply multiply these guys and add them up. And when I do that, so I'm going to get what? I'm going to get an 8. I'm going to get a 4. I'm not going to get a 2 because it is getting multiplied by a 0. I'm going to get a 1. I'm going to get a half, and I'm going to get a quarter. And when you add that up, you are going to get 13.75 as pointed out by Andrew. I absolutely need to say the number, the 10 as well, right? I need to explicitly mention that this is a base 10 or a decimal number. So now I have the correct answer here. The next question that I want to ask you guys is, observe this particular number, 13.75. Could this number belong to octal or base 8 system? Yes, absolutely yes. The reason is octal number system will have symbols 0, 1, 2, 7, right? 0 through 7, absolutely right. 1 is okay, 3 is okay, 7 is okay, 5 is okay, should be okay, right? So that number could also have been a base 8 representation, but because we have a subscript here written explicitly, we know that this is the decimal number system. the point that I'm trying to make is a particular number, even though that may belong to a variety of number systems, its value is different in different number systems. There's a question in the chat box. I'm guessing you wouldn't have asked if it couldn't have been. Yeah, sure. Yes. No. So here, the problem itself was convert base 10 to base 2 to base 10. So I used positional significance to convert the binary number to a decimal number system. And once I did that, I had to explicitly mention that that number is in fact in decimal number system, which satisfies the example criteria. But tangential to that, I said, all right, can this be a base 8 as well? All right, so hold up, guys. Sorry about that. Yeah, she just woke up from her nap and then she just walked into my room. I forgot to lock. Right. Let's see. Where were we? Yes, we were talking about base 8, right? So if I just said 13.75, I don't know whether we are talking about a decimal number, I'm talking about an octal number, I don't know, right? Which is why I need to say, explicitly mention the base or the radix of the number to make it very clear. All right, any other questions about this example? Oh, hold on. What is it? How to know the subscript is in decimal? No, it has to be. It has to be explicitly talked about, right? So, for example, at the top itself, I said base 2 to base 10, right? I explicitly talked about which two number systems I want to do this for. Without knowing the number system, we would not be able to have gone through the example. At this point, I'm going to check because you guys went silent. Can you show how to convert 13.75 to binary? 13.75 to binary. Oh yes, I'm going to show that. Hold on for a few minutes. We are going to do that example too. Next example is, how do you convert base 10 to base 2? 56 base 10 to what base 2? We said we need to do a successive division, right? So this is how I like to do the successive division. I say 56 and then I say, all right, divided by 2, I'm going to get 28, remainder is 0. I'm going to do the division again. I'm going to get 14, again, remainder of 0. I'm going to divide again by 2. I get a 7, remainder still 0. 2 times 3 is 6, remainder is 1. 2 times 1 is 2, and remainder is 1. That's when I stop, when I have everything in binary. And I'm going to read things in the opposite manner, right? So I'm going to read this in that manner. So my answer would be what? 111,000 in binary. Successive division. Keep dividing by 2. I think there are 3 ones and 3 ones and 3 zeros. Yeah, you got to include that as well. Now you can also check this, right? How can I check this? Robert is absolutely right. 1 divided by 2 is 0, remainder of 1. That's how you get that. But you can stop as long as this digit becomes, this number becomes binary. You can stop there. How do you check it? Well, try to go back from 2 to 10, right? Binary to decimal, and you can check it as well. So in order to do that, I'm just going to write the weight of each of these digits on top of them and look at what it makes. So I've got a 1, too big. I've got a 1, 2, 4, 8, 16, and 32. And if I added 32 plus 16 plus 8, I would get 56. And that's how I know that it works. That's how I know I did the conversion from decimal to binary correctly. Now let's move on to hexadecimal representation. Hexadecimal representation is very useful because it's a very compact way to represent things that are in binary, right? It's a very compact representation. Guys, it's already very difficult for me to. I'm not doing hijits. No, I can't. Sorry. Bijit itself is kind of slowing me down. All right. So hexadecimal, in short, hex or base 16, and as some of you have pointed out, 0x. 16 digits. So of course we need 16 symbols. What are those symbols? 0 through 9 and A through F. Total of 16 symbols. And again, A through F, even though they are symbols that complete the hexadecimal number system, their values in decimal are 10 through 15. So A has a value of 10, B has a value of 11, and so on. F has a value of 15. In order to represent any number in hexadecimal format, you would still take each hex digit, multiply with increasing power of 16, where 16 here in this case is the base or the radix, and then finally add things up. That's how you would convert, say, a number in hex to decimal using positional number notation. So for example, if we had this particular hexadecimal number 8A9B, and if we wanted to convert that to decimal, we would take each hex digit, we would start with B, let me do it here, and multiply it with 16 raised to 0. Then we would go to 9, multiply it with 16 raised to 1, and so on. We would move to A, we would move to A, go here, multiply with 16 raised to 2, and finally we can come back to blue, for example. What is 8, 8, 16 raised to 3. Now, of course, in order to do this calculation, we cannot do A multiplied by 16 squared. Instead, we would need to take the value of A and multiply it with 16 squared. So that would be 10 here and 11 for B. And then once we have the values themselves, we can do the addition and then we can represent the number in decimal. So in order to go from hexadecimal to decimal representation, we multiplied by increasing powers of 16 and added them up. What do you think we need to do in order to go back? What would we need to do to go from decimal to hexadecimal? Divide by 16 and take remainders. Absolutely right. Successive division by 16 and take the remainders. What are the possible remainders when you divide any number by 16? What are all the possible remainders? 0 to 15, right? So because we are doing division, I would not get A, B, C, D, E, F. I would get 10, 11, 12, 13, 14, 15. So when 0 to 15, absolutely right. So 0 to 15 would be the possible remainders when I am dividing any number with 16. But for numbers, for remainders that are between 10 and 15, I would be representing them as A through F. Next, let's talk about octal number system. Now this is going to be very quick because you guys understand what makes a number system. When I say octal, you guys think of 8. So this is base 8 or a radix 8. What does that mean? That means that it has 8 symbols. What are those symbols? The octal number system, any number belongs to the set 0, 1, 2, 3, 4, 5, 6, 7. 0 through 7 makes 8 symbols. So any number in the octal number system will have some combination of these 8 symbols. Let's do a base 8 to base 10 conversion. 47.31, it's a base 8 number. I want to convert that to base 10. How do I do that? Use positional significance, meaning I would take 4 and multiply it with 8 raised to, no, not 2, I think 1, plus 7 times 8 raised to 0, 3 times 8 raised to negative 1, 1 times 8 raised to negative 2, and then I would add them up. And if you do this correctly, you should get that particular fraction in decimal number system. All right, questions about this example? Radix is Latin for root, hence the term radical for the square root operation. I see. Oh, well, it depends on how you want to break things up, right? So base 16 is used very often, but sometimes base 8 is also useful. When you want to go down to say 3 bits at a time, then you look at base 8. But you're absolutely right. Hexadecimal is the most prominent one. But if you don't want to have the most compact form with hexadecimal, octal gives you some compactness. No. So base 8 octal number system, because it has 8 symbols, 8 possibilities can be covered by a combination of 2 bits, right? 0, 0, 0, 0, 0, 1, all the way to 1, 1, 1. Like that's 8 combinations. So each octal digit is going to be 3 digits. Do you need to write every single detail when doing the homework? Well, some details are going to be very not every detail, but everything that will convey to the grader that you have understood how to do that conversion, yes. How would you go from base 8 to base 16? We are going to do so many examples, you guys. Hold on with me, all right? So let's do next 20 minutes. Do you guys want me to talk about how to convert base 8 to base 16? Well, you would go from base 8 to base 2 and then base 2 to base 16, right? Base 8 to base 2 would be expanding each octal digit into 3 bits, and then base 2 to base 16 would be grouping 4 bits at a time. So you would do expanding and then combining. All right, I'm going to continue with my examples, guys. Let's spend some time talking about counting things. Can you guys help me count in octal number system? Where should I start? These are unsigned integers. I hope everybody agrees that I need to start at 0, right? What do I do after that? Yes. What do I do after that? You guys get the idea now. Now let's also count in hex. 10 to 17. After 17, you get 20. Right. 0, 1, 2, so on up to 9 is okay. After that, you need A, B, C, D, E, F. What comes after that? 1, 0. What comes after 19? 1A, 1B, yes. 1F, then what? After 1F, 20, yes. You see, the rightmost place or the least significance place, the reason why it's least significant is because it is changing the fastest, right? It has the least weight, or it is the least valuable. As you are, so you cycle through that list for all the possible symbols, then you go to the next higher position, and then you cycle through that. Let's also count in binary. Least valuable. I am trying my best. All right, let's count in binary, you guys. What will help in this example is if we limit the number of digits. So I'm going to limit it to 3. And Andrew has already written the answer. But I want to talk about a little bit structured, a little bit more systematic way to write these binary numbers. So hang with me here. I'm going to do 3 zeros because I'm going to look at 3 digits at a time. And what I'm going to do simply is I'm going to alternate the least significant digit, LSB. And then as I move to the left, I'm going to cut the frequency in half. So 0, 0, 1, 1, 0, 0, 1, 1. And then as I move again, I'm going to cut the frequency in half again. 4 zeros, 4 ones. Now, if you follow this procedure, I guarantee you that filling up truth tables and conversions with regards to binary and looking at octal and hexadecimal, how they relate to binary, will become a lot easier because this is a systematic approach. And that's how you get, right? That would be 0, that would be 1, that would be 2, that would be 3. What is that? 1, 2, 3, 4. These are their decimal equivalent values. 4, 5, 6, 7. Way quicker truth tables. Absolutely right. What comes after 111? 1000. Yes. There was a question earlier about conversion from base 10 to base 2, and this is a fraction. So let's talk about this. How do I convert base 10 to base 2 given this base 10 is a fraction? And the sort of slightly different thing that we need to do over here is essentially deal with the integer part and the fraction part separately. So what I'm going to do is I'm going to deal with the integer part on the left, and I'm going to deal with the fraction part on the right. So for 56, how do I reach 56? I can keep dividing by 2 and record the remainders to convert 56 base 10 to binary. However, because I know 56 comprises of 32 plus 16 plus 8, that's all I need, right? 32 is what? 2 raised to 5. 16 is 2 raised to 4. And 8 is 2 raised to 3. That's all I need, right? For 56. So I would get 1 for the weight of 2 raised to 5, 1 for 2 raised to 4, 1 for 2 raised to 3. That's it. After that, I'm going to have 3 zeros for weight 2, 1, and 0. So that would be my integer part conversion. I'm done with that. Now for the fraction part, here is when you will see something different. What did we do for the integer part? Integer part, we had positive exponents of 2. So we did division by 2 successively and recorded the remainders. However, for the fraction part, we have negative exponents of 2. So when we do that divide successively by the negative exponent of 2, we literally are multiplying by 2 every time. So that's what happens in the fraction part. We take 0.34 and we multiply by 2. Why 2? Because we are converting it to binary. We get 0.68. We are going to take this number and keep going. 1.36. We are going to drop that 1 and only take the fraction part from before and keep multiplying by 2. Successive multiplication by 2, and while we are doing that, we are recording the integer part of the result. And then this can keep going. Which also has other consequences, right? The other consequences, such as if you are trying to express a certain fraction, you may or may not be accurately represent rounding errors. Absolutely right. You get it. You got it. Yes. So it depends on the number of bits that you have associated for the fraction part. All right, let's fill out the answer now. For the integer part, we are good. 111, 000. Brilliant. 1 1 1 0 0 0. Then we have got the binary point. Then we have got 0 goes there, 1 goes there, 0 goes there, 1 goes there, and then we have the last 0, and this continues. More number of digits for the fraction part, the better the accuracy, less rounding errors. So what did we do here? If I had to describe it in terms of a statement, I would say I did multiply by 2, keep recording remainders, keep recording integer part. Also make sure that when you actually take it down to the next multiplication, you throw away that integer part. You know, you can actually prove this sort of conversion between decimal and binary using a proof, an analytical proof. And if I have time, I'll do that proof and give you guys a small video to watch. But you can actually prove that this works analytically. Now we talked about how to convert base 10 to base 2. Now how about base 10 to base 5? What would be different? Divide by 2 successively and record the remainders. Multiply by 2 successively and record the integers. What changes here? We should be dividing by 5 successively and record the remainders, and we should be multiplying by 5 successively and record the integers. So let's do that quickly, and because we are doing it by 5, it doesn't take that long. So I have 56, I'm going to divide by 5, I'm going to get 11 with a remainder of 1, and then I'm going to get 2 with a remainder of 1 as well. And because I have 2, 1 and 1, all of these belong to the base 5 number system. So I can stop here. So essentially this would be what? 2, 1, 1, base 5. That's my integer part. I'm done with that. Keep dividing by the base, record the remainders. For the fraction part, I have 0.38. I'm going to multiply this by 5. I'm going to get 1.9. I'm going to get 0.9 times 5. I'm going to get 4.5. I'm going to take 0.5 times 5. I'm going to get 2.5. I'm going to take 0.5 multiplied by 5 again. I'm going to get 2.5. All right, so this is going to keep going. How many sig figs does a double use? Double precision format. It has 1 bit for the sign. It has 23 bits for the exponent, and I believe it has the remaining 53 or whatever bits for mantissa. This will keep going. So what would be our answer here in base 5? 211, a point in the base 5 system, and then we would get 1, 4, 2, 2, and then that 2, the sequence of 2's keeps going. And that would be our answer there. So hopefully, you guys are building up skills that will allow you to convert from any number system to any other number system for unsigned integers and fractions. Can we do this? Let's try to convert a base 16 fraction to decimal. What should I do here? Any number to decimal. What do you guys think of? Oh, it's 52, right? Right. For 32-bit, I think it's 1, 8, and 23. For 64-bit, I think it is 1, 11, and 52. 1 for sine, 11 for exponent, and 52 for mantissa. All right, so divide by 16, get no. We are going from 16 to 10. So any two decimal use position significance. Multiply by numbers by increasing powers of 2. 16. Yes, absolutely right. You got it. So we do 8. What do I have here? This is 16 to 0, 16 to 1, 16 to 2, 16 to 3, 16 to negative 1, 16 to negative 2, right? So what that would that be? 8 times 16 to 3 plus, should I write A? Maybe not. Is it 4096? All right, I can't do that calculation so fast, guys. 8 times 16 to 3, 10 times 16 to 2, 9 times 16 to 1, 11 times 16 to 0, 12 times 16 to negative 1, 15 times 16 to negative 2, whatever that is. It would be a fraction. How are you getting? Hold on, what? So 4096, is that the integer part or? All right, so here you can use a calculator, find this out. Number crunching at this point. How do you do base 10 to base 16? Last example for today. Base 10 to base 16. Divide by 16, record remainders. Perfect. Very quick. 46 divide by 16. 2 will give me 32 with a remainder of 14. And what is 14? E is absolutely right. So your answer would be 2E. Maybe I can do better with the 2 here. And in order to check 2E to base 10, what do? You do E times 10, E times what? Not 10. 16 raised to 0 plus 2 times 16 raised to 1. I cannot write E, I need to write 14, right? So when you do that, you get 32 plus 14, you get your 46. So you can check it as well. It's going by from, if going from base 2 to base 5, for example, is there a faster or easier method than going to base 10 first? It's not. I get this question many times. But unfortunately, there isn't a very quick way to do that. So when you are going from base 2 to base 5, you would go from base 2 to base 10, then 10 to 5. However, there are special cases that are applicable for bases that are powers of 2. For example, base 2, base 4, base 8, base 16, base 32. We can do some interesting, faster, quick things there. However, for base 5, base 3, base 11, base 9, we can't do much but to go to base 10 as a means to convert one to the other. It's past our class time, so what I'm going to do is stop here and I'll pick it up over here when we come back.